Here we are. All right. We are 7. And today is a tough lecture. So you better come, send a WhatsApp message that today is a lecture for real physicists. So if you miss this one, it's going to be tough. All right. So let's start right away because we have no time. So I'm going to, so I want to let you know that I'm updating the Canvas site all the time with, I updated, for instance, the lecture from yesterday. I added a few more slides here. You can see this, the lecture, the PDF, which is the one we have here. I just improved things. And yesterday we briefly mentioned the fact that we have a fission which accompanies is accompanied by beta decays as well. But first we have a fission and we have a chain reaction because a neutron, this uranium-235, is very heavy, has lots of protons, and the repulsion is, he has a very subtle equilibrium, and just a little touch will make it split into two, right? So this will be the uranium-236, and the splitting of the nucleus into two fragments, which we mentioned yesterday. They are krypton-92, barium-141 for this particular case. But as you can see also, there's the emission of 3 neutrons. And these 3 neutrons, again, will hit another uranium-235, right? And the same process will happen. And again, 3 neutrons will come out, and the same process will happen, and so on and so forth, with the final result of creating a chain reaction, right? So then, once these guys are produced, the krypton and the barium, then we have these beta decays. And yesterday we didn't mention, for instance, what kind of energy spectrum do we get from this. And let me set this up nicely so we can write things down. So basically, we want to go here. And I always mention that we have the neutron is converted into a proton plus an electron plus an antineutrino plus there's a Q value for the reaction for that beta minus, right? Because you have an electron. Or we have the other situation, protons converting to neutrons plus a positron plus a neutrino plus again a Q value for that beta plus, right? Because we have a positron here. So then here the charge here must be the same, right? Also the angular momentum must be conserved, and the energy release is not so much of the kinetic energy of the nucleus because it's very tiny compared with the energy released by all the electrons and all the neutrinos coming out. And this is the typical spectrum that you see for the release of that energy, for all these neutrinos and all these electrons coming out and decaying all the time to reach that value of stability. Those black squares in the charts of nuclei, right? These fellows here that we have seen many times, right? All these black squares. Everyone is trying to go to that minimum energy, which is reached when you reach those stable nuclei like zirconium-92 or praseodymium-141. So this is the energy release, and it looks like this. And there's an electron part which is dominated here, and the energy release by the antineutrino for the case of the beta minus, right? And finally, you have the Q value. The energy of the Q value is the maximum energy you can reach by the release of energy according to Einstein's formula. And basically, that is the energy produced by electrons, but there's also more energy that it is produced after the the beta decay is already happening, right? And then we have a gamma ray radiation, because then you need to de-excite the nucleus, the mother nucleus, right? So the parent decays by beta particles, by neutrinos or antineutrinos, depending on which beta decay. And then it goes to the daughter nucleus. And then there's an additional emission of gamma radiation, which is an electromagnetic radiation with high energy. In this case, is 1.345 MeV. 1.345 MeV or 1,345 keV. And this is not always, this is a very simple case, but you can see here in another beta decay that things become complicated, and there's a lot of gamma radiation coming to reach again the strontium 80. And this is the case. And then again, it will go to a nucleus which is stable, right? So the whole process is illustrated here. We have the beta decay, and then we have the typical energy spectrum for the electrons and the positrons, or the electron antineutrino, positron, and neutrino, depending whether you have beta minus or beta plus, respectively. And then you have the emission here of a positron, and here is the energy spectrum when you decay from copper 64 to nickel 64. And then you have the additional gamma radiation. And I want to tell you here, this is a very particular case, although there are many of those, where 64 copper can actually decay here, right? Or by electron conversion, or decay here by beta minus, right? Here you have the extra proton, here going here you have the extra neutron. So that's why decaying to zinc 64, you have a proton, a neutron actually converted into a proton, plus an electron, plus an antineutrino, right? So now our purpose today is, this is a very characteristic spectrum, and it's not a unique, it doesn't have discrete levels, but the energy is shared, and that's why you have a continuous spectrum between the kinetic energy of the recoil nucleus, which is very tiny, as we mentioned, the beta particle, and the neutrino. So this sharing yields a non-unique characteristic energy, because, for instance, in this particular case, we know that 1345.7 is the gamma ray energy of nickel 64. So this is a fingerprint of nickel 64. This particular radiation coming from a J angular momentum, total angular momentum 2, with positive parity, and decaying to the ground state of nickel 64, which is an even nucleus. And in even nucleus, the ground state is always 0 plus, because proton and neutrons couple to each other in Cooper pairs, and basically, according to the Pauli principle, you have the spins up and down to avoid having the same quantum numbers, right? So all these are information that we'll go through slowly, and probably we won't have time to go into detail. And today, I want to explain a little bit on this. What about the gamma ray radiation? So what kind of radiation is this one here? It looks like an arrow, but it's not really an arrow. It's just a way to illustrate that this level, this particular characteristic excitation in nickel 64, decays from a 2 plus state to a ground state 0 plus, right? And that's it. Nickel 64 is stable, and the process will stop right there, right? So any questions before we have a little bit of real physics? Guys, questions to the chat quickly. Okay, if not, we're going to continue. We are going to continue, and we are going to continue trying to investigate that electromagnetic radiation, because we're going to talk about dipole, quadrupole, you know, and I want you to understand a little bit where this concept comes from. So we're going to go step back into electromagnetism, and we're going to go back to, let me actually make this a different color here. So let's say that we have a charge distribution. Okay, and we have obviously we have a system of coordinates, right? Which is, this is Z, this is X, this is Y, right? And then we have charges. We have a charge distribution, as I say. This is say Q1. We have Q2. We have Q3. We have a bunch of charges in a volume V. Let's call it V prime. So then we want to investigate what is the electric field at a point P. So that electric field is going to be characterized by a vector R, and it's going to be the electric field generated by this particle, which we're going to call R1, the vector. And as we know, the distance here will be R. Let's call it R1, which will be R1 will be equal to R minus R1, right? So now we want to know what is the electric potential here, or the electric field at this point P. So as we know, the electric potential is defined by R, the sum. We're going to sum the sum of all the charges to the n, and then we have Qi. Here we have 4 pi in epsilon naught. And then here we have Ri, right? So what we're going to do is to decompose this potential, this electric potential, into different quantities, which will allow us to look into more detail and trying to reduce the complexity of the charge distribution. Remember, this may have lots of charges everywhere, right? So this charge distribution, we are going to reduce it into some quantities, which we are going to call distribution, which we're going to call multipoles, right? So basically, we're going to do a multipole expansion of the electric field. The same thing of the electric field. The same thing can be done with the magnetic field. Sorry. Write it down properly so you don't get confused here. All right. The same thing can be done, but for the magnetic field, you have to use the potential vector, which is given by 4 pi mu. Is the susceptibility, actually the other way around. Remember, mu 4 pi mu 4 pi, and then the volume here, the current as a function of R, divided by that R in that volume. All right. So we can apply the same thing to the magnetic field, but we're going to use it for the electric field right now, because normally the electric transitions, these electromagnetic radiation, which is coming out of that beta decay or out of any nucleus being de-excited, it will have a particular name, a particular physical meaning, which we're going to deduce in a little bit. So for that, let's focus on this, and then we need to get this as a function of quantities that that makes sense as a function of r, small r, and a function of ri. Let's call it in general ri. So basically, we can do this, and every r going to add. Eventually, this is going to be ri. Actually, let's call it, yeah, that's fine. So then we have to do that. Let's actually do one thing here. Let's do a little bit of trigonometry, and let's say we have a triangle like that, and this is going to be our r. This is going to be our the small r, and this is going to be the r, which we can call it r prime. Let's call it r and r prime, but this will be r1. Let's say ri and ri prime. So the prime basically refers to the charges, and this guy refers to the point where we want to measure the electric field. So then we can deduce from using Pythagoras. Actually, we can deduce this is the angle alpha here, which we are going to call the same angle right here. I'm just doing that separately so we know, we make things a little bit clearer. So so basically, according to Pythagoras, we have the r squared, right, is equal. So this is total r. So we are going to take this triangle here. See a little bit the color. We're going to take this triangle right here, right? And we're going to apply Pythagoras to this particular triangle. So basically, we can say that this is r minus this little bit here, which is r prime cosine of alpha, r minus r prime cosine of alpha. Let's remove the indexes for the time being. Square plus r prime. Let's make an angle here. What is this? Let's call it gamma. R prime cosine of that gamma. If we extrapolate this triangle, we're just doing basic trigonometry here. And we bring this up. Need to be a little bit more straight here. So what is here we go. Right, if we go up, this angle here will be the same. This angle here will be this guy here, will be alpha. And this angle here, although it doesn't look like, but it's supposed to be gamma. And then obviously this whole thing, this alpha plus gamma will be 90 degrees. So basically gamma will be 90 minus alpha, right? 90 minus alpha. So then the cosine, we know the cosine of 90 minus alpha will be actually equal the cosine of 90 cosine of alpha, which is 0, minus, so it's plus the sine of 90 sine of alpha. So basically this is 1. So this remains at the sine of alpha. So then everything is as a function. This r prime cosine of alpha, or gamma actually, becomes r prime sine of alpha. Sorry, not gamma, but alpha. Okay, so we just we have that equation, Let me just close this. We have that equation open. I want to get a new one. All right. So basically we have that R square is a R minus R prime cosine of alpha square. Let me see if we can remember that. So R square is equal to R minus R prime cosine of alpha square plus R prime sine of alpha also square. Remember, this triangle looks like this, and we just prove that this angle here, this alpha, the cosine of gamma is equal to the sine of alpha, right? And this is alpha, this is R prime, and this is R. Right, so basically we just distribute, we just open this up and then say, okay, R square plus R prime square cosine square of alpha minus 2R prime cosine square of alpha plus R prime square sine square of alpha, which is basically R square plus R prime square cosine square plus sine square is equal to 1. So it's R prime square minus 2R prime cosine. Here there's no square cosine of alpha. All right, and we reach the this rule for the cosines. Obviously, what we're interested is in R, so R will be R square plus R prime square minus 2R prime cosine of alpha to the 1/2, right here, square root of that basically. And then we go back to our potential. V of the R will be equal to the sum of all the charges from 1 to n number of charges, Qi 4 pi epsilon naught R, which will be equal to the sum of I equal 1 to n Qi 4 pi epsilon naught. And then here we have R square plus R prime square minus 2R prime cosine of alpha to the 1/2. And now let's work out this denominator here. And let's take out R, which is the distance from the center of coordinates to the point where we want to measure the electric field. And this will be equal to, let's just take the denominator, and that will be equal to R1 plus R prime R square minus 2R prime R 2R prime R cosine of alpha, right, to the 1/2. So this is basically this denominator here. And now assuming that this point, the point R, I mean the point is R is always much bigger because R we can move it, you know. The whole point of this expansion that we're going to do now is assuming that the point where we determine the electric field is far away from the source charges. You know, the R basically R prime, and this is charge prime, whatever. Basically, R is always bigger than R prime. Assuming that, we can make a series expansion, power expansion here using binomial expansion, and we are going to assume for that this is T, And basically, we're going to make this potential equal the sum of I equal 1 to n q I 4 pi epsilon naught r. This r, we're going to put it there. And then it is going to be multiplying r, 1, this whole term here, right? So 1 plus r prime r square minus 2r prime r. You interrupt me if you want to, just let me know, because I'm focused on the calculations. I cannot see you what you're writing up in the, this is goes to the -1/2 because now we move it to the numerator, right? So basically we are going to get this as a t, as I mentioned before. So we are going to expand this as a series of terms, right? And this is going to be 1t minus 1/2, which is given, this is a typical binomial expansion. And I have, I'm doing this. So I have a book here. You have all the Taylor expansions, and you know, this in particular is a binomial series, is given by one. What is the cursor here? 1 minus t/2 plus plus 3/8 of t4, right? Let me see. This is binomial expansion plus 1 3/8 of t4 minus 5/16 of t cube plus, you know, all the terms that we want to go through. But as we shall see, what we know of in a Taylor expansion, the first terms always dominate. The first term dominate over the second one or the third one, and we're going to see that right now once we develop these equations. So let's see where we are now, because we need to know that now this is t. What is the cursor here? There we go. So this is t, we say. Oops. Over there. Yeah, move somewhere. Yep. Oh, here we go. Go back. All right. So now, basically, if you change this into here and change these numbers, you will get to the point where the potential is given by different terms. And these terms, let me see here. We just need to change this t, 1 plus t minus 1/2 into this, but knowing that t is that factor there. And basically, we are going to get a VR, which has a 1/4 pi epsilon naught r, and then the sums of I equal 1 to n, or the number of charges, qi. And this will be our monopole term of the electric potential. And basically, it defines all the charges that we have. It's basically the charge of the system. Then we have another term, which will be 1/4 pi epsilon naught r squared. And you check, this depends on r. Obviously, this depends on r squared. So you already know that the weight of this second term will be smaller than this one here. And this will be the sum again of I equal 1 to n and all the charges, and this will be the dipole term, which is characterized by, I want you to do this yourself, Qi Ri cosine of alpha I, right? And this is called the dipole term. Dipole, this is the monopole, the whole thing. The monopole term, plus there will be a quadrupole term, which again will be 1/4 pi epsilon naught r cubed. And the sum of all the charges from 1 to n. And in this case will be Qi Ri squared over 2. And here we have the typical 3 cosine square of alpha I minus 1. Plus other terms, this is going to be the whole term here will be the quadruple term. And it will tell us what kind of charge, what kind of shape the charge distribution has, right? So all these terms now they have a physical meaning, and we have basically dissected the difficulty, the sensitivity of the charge distribution that we have originally into these different terms. And again, this one has r cubed, which will be smaller than r squared, and this is r, right? So now, how do these guys look like? So this is obviously the charge. The dipole, how does the electric field looks like? So the electric field in a dipole, let's call the dipole like this, it will have the typical field lines, which will look like this. And basically, it will have a radiation or equipotential lines, which will look like that. These are the potential, equipotential lines, right? And this will be the radiation of a dipole. So pointing up and down. Okay, this is very important because in a nuclear reaction, we can determine what is the radiation coming out of a transition once the nucleus gets excited, and we're going to go through this a little bit later. For instance, we have a 1 minus state decaying. This is the weakly arrow to ground state. There's a gamma radiation. What kind of properties this has, as we're going to see in a little bit, this will be a dipole, and this will be a electric dipole, a pure electric dipole. So it will look like this. So basically, if you want to know what kind of radiation, and this is how we determine in many occasions what is the parity of the levels of the states and what is the radiation when a nucleus de-excites by emitting gamma radiation. If we have a quadrupole, the quadrupole again will look like a little bit different thing. Will look like still you have this blob of radiation, and then you have also blobs. Basically, these are emission of gamma rays going up and down, and also on the sides. Okay, this is how these terms that we're going to introduce now: dipole, electric dipole. We call it electric dipole will be an E1. Electric monopole, which comes before monopole, will be an E0. Electric quadrupole will be an E2. Octupole will be an E3. And so on and so forth. But these are basically the main radiation, radiation that you will have from the electric field, but also you will have a magnetic one, which will come as a M1, M2. Actually, this is the dipole. The monopole will be M0, but no one has ever discovered an M0 monopole because as I mentioned before, the monopole describes the charge, is basically describing the charge of the electric field. As you can see, What is my here? As you can see here, right? So here we go. So basically, this gives you the charge. And there's no such thing as a magnetic charge, or hasn't been discovered yet. So that's why the M0 doesn't, no one has ever found an M0, right? So then these are the typical radiation that you're going to have. So we can go back to our presentation now and say, okay, this fellow. So 2 plus to 0 plus, what kind of radiation is that? You know, it's not an arrow of radiation. This is a radiation being emitted in a particular way, right? And now we're going to set up the selection rules for electromagnetic radiation from one excitation to the other. Guys, any questions? This is today we are a little bit more serious. So we are going to set up the selection rules. We're going to call this whatever order of multipolarity, E1, E0, E2, E3. So we're going to set up some rules. For instance, let's say we want to discover what is this 2 plus to 0 plus. So we have different rules. So if there's if parity does not change, the multipole expansion that we have starts with an E0, then follows an M1, then follows an E2, then follows an M3, and so on and so forth. If parity change, then we are going to start with a M0, which, as we know, no one has ever found. Then we have an E1, then we have an M2, then we have an E3. And we're going to set up some selection rules. So each of these numbers, let's call it the lambda, the multipolarity, let's call it lambda. So the selection rule will be that this is J J initial, let's call it J initial, this one, in initial angular momentum, this is the J final. So J initial minus J final in absolute value will be less or equal than the multipolarity, less or equal than J initial plus J final. So according to these simple rules, we have this and we have that. So we can do this one here, for instance, 2 and 0. 2 minus 0, 2, less or equal than lambda, less or equal 2 minus 0, 2. So lambda can only be 2, right? It's defined, it's a stretch 2. There's nothing you can do there because this is a 0. So this is a 2. There's no change in parity because this is positive and this is positive. So what do you think it is? There's no change in parity. We go here and then we start counting 0, 1, 2, right? This one. So this radiation is a E2. So it's an electric quadrupole, and that's it. Cannot be anything else. So any questions? So this is very, very simple. Looks complicated so far. So we have gone through the multipole expansion. We have deduced the dipoles, their quadrupoles, and each term plays another important thing is that the electrics are always stronger than the magnetic, but not the other way around, obviously. So if you have an M1, for instance, it will be normally accompanied by an E2. But if you have an E2, the next one, the M3, will be negligible. Okay. So let's say, let's give another example. This was 1. Let's make it another one, 2. I was saying before about this 1 minus to 0 plus, right? So what kind of electromagnetic radiation is this one. So there's a change in parity.
That was really tough.
Who is in the which? Anyone saying something? Someone is talking.
And the mining, how bad it is.
No, toxic is an understatement.
That's what you said.
It was really bad. Hence, even now, I have no desire.
Hello? Anyone is talking in the background? So okay. So 1 minus to 0 plus. So what do you think is the electromagnetic radiation coming down?
I was introduced by.
Let me see.
How did you manage
There's
to get
some
out of
comments
it?
here.
I know
Because that's not who I am. You know the saying that says, the
Guys,
company,
Asile,
determines
we need to mute her. All right, muted. So questions is a 2 plus. Okay, so very good. It is J1 is 2 plus, yeah. So 2 plus, did professor say J was the angular momentum? Yeah. So J is the total angular momentum. Keep asking questions. So J, remember we introduced J before. So J it was equal to the total angular momentum L plus minus S, right? So it gives us an indication of the orbital angular momentum and how the spins couple to each other. But we'll go through that a little bit better when we go through the shell model and we learn what is L. But so far, let's say is the total angular momentum of the state in particular. And anyone can tell me what is this? 1 minus to 0 plus. So basically, we are trying to understand. We have a bunch of radiation coming down, and we have a bunch of states. 3 plus to 2 plus, 4 plus to 2 plus, 2 plus to 0 plus. And these are all arrows, but in truly they're not arrows, right? This is really electromagnetic radiation. And this electromagnetic radiation will look like this, with 2 blobs pointing up and down, and actually they will be more like this. Let's draw it properly. 2 smaller blobs on the sides and big blobs on the left. On the small blobs on the sides, this emission this way and emission that way. So the gamma rays are not going like in one direction here, but they are being emitted in a particular radiation blob. As we can see here, this is how the electric field is determined for this particular case. And here we have a parity change. So if parity changes, we have, again, let's do it the same trick. 1 minus 0 is 1. Lambda 1 plus 0 is 1. So basically lambda is equal to 1. So 0 and 1, right? So is this an E1? This is very easy. You just apply the selection rules and this guy will look like this, right? All the gamma rays will be emitting up and down. So this is very interesting because we can go to the lab. We can go to our new beautiful array spectrometer called GAMCA, the lion. And GAMCA, the lion, has lots of detectors at different angles, right?
Prof. Nico?
Yeah, tell me, Shoki.
Can I ask, with the 1, moving from the 1 minus to the 0 plus, why is it that when you substitute for the angular, you don't consider the negative on top? Doesn't that tell you that the parity changes? Because it seems like we did it the same for when the parity didn't change.
No, we go here. I noted here, if parity changes, then we do the same thing as we did here, but in this case will be 1 less or equal than lambda less or equal than 1, right? So lambda will be 1 no matter what, right? So parity changes, we go here and then we do the same, 0 and 1. So this is the resulting E1, which I'm writing here. Before we went to the if parity does not change, right? Before, for this guy in particular, there was no parity change. So we go here and we count 2, 0, 1, and 2, right? And cannot be anything else, but we're going to go now to a case where you have different possibilities. Is this clear, Shoki?
Okay, yes, it's very clear. Thank you so much, sir.
No worries. Ask always questions because this is the
excuse me, Prof. If the parity has a negative on top, which means it does change.
No. What I mean, there's a change from here to here, right? This
Yes.
negative
Yes.
and this positive, right?
Yes.
If they are both negative, there's no parity change. Okay.
Okay.
If they are both positive, right? So then we have these reactions that we have our beam incoming, and then we have a target, and then we produce a nuclear reactions. So nuclear reactions align the nucleus in a way that the radiation is being emitted, with respect to the plane here in the center. So basically, we can deduce if we have something like this, right? The radiation comes all over the place. But it seems like the radiation goes more here for this particular decay. Say we want to know what kind of a state is this one. We want to deduce. We don't have much of information, but we suddenly explore and say, okay, this guy is there and is decaying by a dipole. So the only way, so then we apply some Sudoku, also some kind of logic. So in the only way this radiation to happen only at these degrees, at 90 degrees, is because the radiation is happening like this here, right? It's going up and down. So we have a dipole transition. So this dipole transition, we deduce is an E1 by looking at how the radiation look in our detector system, right? That's why it's very important to have an array with many detectors so we can pin down the sensitivity of this electromagnetic radiation being emitted by the nuclear reaction, by that state in particular that we have excited, and going down to always to the ground state. So if this guy, instead of that, it looks like suddenly we have something else, and wow, it looks like we have a radiation like this, but then also we have a little bit of radiation on this side. So then we start having some radiation here and here and here. So this particular radiation, which we'll be seeing almost everywhere, but mainly here and here, right? So this will tell us that this guy is actually a quadrupole, and we can deduce that we have an E2. So basically, by the more angles that we have, because the different radiation will have more complications, the octupole will look different. The magnetic will look a little bit different they will have different properties to the electric, but again, they will be emitted up and down for a dipole, magnetic dipole. So you see, this is very interesting to see how you are looking at how the radiation is being emitted from the nucleus, from that particular state. And then we can determine the properties of nuclei once we characterize all this electromagnetic radiation and we provide angular momentum, excitation energies, and all of that. So let's try to go a little bit more. I'm going to show you a couple of more examples. I'm sure there will be in the test on Friday, there will be a question like this, where you have to deduce what is the electromagnetic radiation from different states. The populating, you are the exciting this guy going to this guy. What kind of radiation? How does it look like? So, for instance, let's go to this one here. So we have let's do this one. This is a particular case. 0 plus to 0 plus. There's no change in parity. So we have E0, M1, E2, M3, and so on and so forth, right? So this is a particular case because there's no gamma radiation. So is J initial minus J final is 0, right? 0 minus 0 is 0. Less or equal than 0 is going to be 0, J initial plus J final. So basically, this is 0 and this is 0, but any radiation, any photon, at least, you must have a angular momentum. It carries an angular momentum of 1. So you cannot have a gamma radiation for this particular And this is the only case for this particular case of 0 to 0, right? So just because the condition that a photon at least must carry a gamma or a photon energy, any photon must carry at least 1 unit of quantum or angular momentum. So the units in angular momentum are generally defined as h bar. So whatever is the number, so J is whatever 2, even if we say 0 here, or whatever we say is that 2, is normally 2 h bar. So another example. Let's go now, for instance, this 2 plus. Let's make it a little bit more complicated to 2 plus. So now we have the same situation. Actually, there's no change, no parity change, right? But now here we have a different case. So it's 2 minus 2, 0. So we have 2 minus 2, 0, right? Less or equal lambda, less or equal 2 plus 2 is 4, right? So then the multipolarity can be 0, 1, 2, 3, and 4, right? So then we go here. We know that there's no 0 for gamma radiation. This may decay by electron, but not by gamma. So we are interested now in the electromagnetic radiation. So then we'll have M1, 1, so 0, 1, 2, 3, and 4. E4, right? So this one doesn't play any role. Then we have the magnetic, which is good. Then, as we say, we have the electric, which follows. Every time we have a magnetic, follows with electric, because the electric is always stronger than the magnetic. But now that we have the electric, the magnetic doesn't follow, because the electric is much stronger than the magnetic. And obviously these ones don't follow either. So this transition here, it will also decay by an E0, which will be a electron decay, but the electromagnetic radiation will be a mixture of M1 and E2. So this will be let's call it a mixture. So it won't be a pure dipole or a pure quadrupole. And there are ways to determine this kind of a mixture, on the electromagnetic radiation. And this is just a concept called the delta, the mixing ratio. But for this, you don't need to know right now. Next year, if you want to know more, you will learn how to determine the mixing ratio, which will allow us to exactly pin down what is the proportion of that M1 and E2. For instance, the percentage of M1 is, I just brief you a little bit. The percentage of M1 transition will be 1 over 1 plus delta square, whereas the percentage of E2 will be given by delta square 1 plus delta square. So these measurements are very important in nuclear physics. And again, the sensitivity of having an array like GAMCA will allow us to measure precisely these mixing ratios. And here I want you guys to get excited, because this is a work of almost 10 years. If you go to our webpage and you click here on GAMCA, this was the largest single grant ever given by the National Research Foundation in a competitive call. It was 35 million rands given to UWC. And we have a consortium of teams of universities, Stellenbosch, Leeds, University of Zululand, Denver Labs. And you can see here a little bit of the story of GAMCA. There's not much to, I think it should upgrade this web page, but you can see, NRF funds state-of-the-art nuclear spectrometer for UWC. So this is something to be excited, because after almost 10 years of work, we are going to start running this new facility at the Temba Labs from next month. So we have finished the work. UWC has proven the world that we can achieve things, and this was a huge competition to get this money. We have all the universities, UCT, UP, Stellenbosch, they were all trying to compete for that money, but we got it all and we made things happen. So with that, I finished the lecture for today, and I open this session for questions. So,
sir, can you please repeat how you got the mixture from the 2+ state to the 2+?
So let me share the screen again, Shoki, and I'm going to give you another example. Okay. So I'm going to give you another example. All right. This is just always a matter of applying these very simple rules of electromagnetic decay. All right. So let's, for the 2+ to 2+, I'm going to repeat this, or probably you can go back to the video and watch it again. But let's make it something even more complicated. 3+, let's make 3+ to 3+, ¿vale? So 3+ to 3+, again, we go first and we say, okay, J initial minus J final less or equal than the multipolarity lambda J initial plus J final. So initial 3 minus 3, 0, 3 plus 3, 6, right? So lambda can be anywhere between 0 and 6. So we go, and there's no change in parity. So then we start from E0, M1, E2, M3, E4, M5, E6, whatever. It's just we're getting too much, because remember the weight when we went through the multipole expansion, the weight of every additional multipole is always smaller, because the first one is 1 over r, the second one is 1 over r squared, the third one is 1 over r cubed, right? And so on and so forth. So what is this radiation here? What is this gamma radiation here? So we have, it can be any of these guys, 0, 1, 2, 3, 4, 5, and 6. However, because of the properties of the Taylor expansion, of the binomial expansion that we did before, we know that E0 doesn't come with gammas, because the gamma always need an angular momentum of 1 unit. So this will decay by electron conversion. So there's no gamma radiation being involved in an E0. This guy will be good, M1. Remember, whenever we have an M1, we also, the electric also comes, the E2 will be good. But once we have the electric, the rest can be considered negligible. Once we have the electric, heating the magnetic M3 is negligible. So this transition will be again M1 and E2 mixture, right? These ones again will cancel, will be negligible terms in the expansion compared with these two guys. So if we have an electric, let's say another case here, 3 minus 2, let's say 3 minus 2, 0 plus. Okay, so again we do 3 minus 3 minus, well, this is clear. This is 3 less or equal than lambda less or equal than 3. So this must be, there's a change of parity. So M will be M0, M0, E1, M2, and E3, right? So they will be 0, 1. We know that this doesn't exist or hasn't been discovered. 0, 1, 2, and 3. So there's only 3 possibilities, so it's this one, right? So it must be an E3. So, but let's look at this one, another one, for instance, 3 minus 2, 2 plus. Again, this will be the sequence because we have a parity change, M0, E1, M2, E3. But then in this case, we will have 1 less or equal than lambda, less or equal than 5, right? So then let's see the possibilities. M0 doesn't exist or hasn't been discovered. M2, E3, M4, E5. So let's see what this case in particular. So 3 minus 2, 1. So 0, 1. That's it. The rest we cancel out because once we reach the electric, the magnetic is much smaller. And this term, because it's higher, will be smaller. And this, because it's higher, will be smaller. And this even much smaller, right? So this transition is only, despite all the possibilities that we may have, is only an E1 because the next one is an M, magnetic, and then that is negligible. So basically you go through the video and it's very clear, it's very simple. You know, if you have a change of parity, you go and start with this sequence here, right? Everything is really, really simple. First you check what is your J initial plus minus J final, J initial plus J final, all the possibilities for lambda. Then you look, there's a change of parity. Okay, there's a change of parity, so we go here. Right, if there's no change of parity, we go here. And we start counting all the possibilities that we have. You know, 0, 1, 2. If we reach the electric, okay, the rest, forget about the rest. So, okay, is that clear?
Yes, sir. Thank you so much.
Excuse me,
Okay.
sir. It is always the case when we read the first electric, we must ignore the rest of the magnetics.
Right, so whenever we reach an electric, the magnetic is always smaller, and then the rest of the terms also cancel out because the Taylor expansion, remember, this is important. I'm going to leave you now because you have the tutorial. Remember when we describe the multipole expansion, that's why we did it. We have these terms, right? This term here, the first one, which is the charge, basically the sum of the charges is R, 1 over R. This one goes at 1 over R squared, and this one goes over 1 over R cubed, right? So this term will be strongest term. This one will come next, the dipole. This one will come next, the quadrupole. But the next one will be 1 over R to the 4, right? Whatever, 1 plus R to the 5. Also, I want to remind you that this P0 of x is equal to 1, P1 of x is equal to x, and P2 of x is equal to 3x squared minus 1. So basically, these guys are called the Legendre polynomials, just for you to remember, and so on and so forth. So if you know the properties of the Legendre polynomials, you can always deduce what is coming here on the R5, on the R4, because it's clear that this term will be the same, but adding 1 more R, right? So these other guys will be the same. So if you know what are the Legendre polynomials, you know what the next terms are. So this may be important. This may be important because you may have something which looks like some strange cases, but something which looks like this, you know, like a 4 plus to 0 plus. And sometimes this is very rare, but it may happen. You know, it may happen, and you need to know how that will look like, how that transition, which will be M0. Let me see. There's no change of parity, so we start from E0, 0, 1, 2, 3, 4. That will be an E4. Let me see, 0, 1, 2, 3, 4, right? That will be an E4, which is very rare, but we need to know how the radiation looks like. We know that these guys look like this, right? The M1, E2, there will be a blob here. This guy is more like an octupole. It will look more like a something like this, whatever. This one will look more like this, the radiation up and down. So basically, it's important that we know the mathematics, so we know what kind of radiation we are expecting, and we can determine the physics. We can deduce the physics and the discoveries. They must be solid. We need to know the mathematics and the physics before we can claim, okay, we discovered this transition, which is an E4, and no one has ever seen as an E4 before. So I leave you that with that here. Go through the video. Today I will share the whole video, and you can go through the different examples that we have done at the end. And now I have to leave Craig with some time for the tutorial. All right, guys. Thank you again for this lecture, and I'll see you on Friday is the test, and Monday, the next lecture. All right, thank you so much.